Dear participants, energy is the prime mover of socio-economic growth and technological advancements across the globe, and therefore plays a crucial role in the prosperity of human life. Economic growth in South Asia can only be ensured by making energy accessible to all at affordable price and on sustainable basis. A holistic view of the energy situation in the South Asia reveals that optimum utilization of the resources of the region needs to be prioritized, since it would ensure and endure energy security and maximize the socio-economic benefits for the people of this region. As a result of economic growth, the degradation of environment is a big challenge and cause of concern. Waste management is currently a major issue worldwide with numerous environmental implications. Waste to energy is usually understood to consist of a broad range of approaches and techniques, including incineration, pyrolysis, gasification, anaerobic digestion, and co-combustion. However, its integration in developing countries, especially in South Asia, is often faced with skepticism and a complex set of barriers which are quite unique. Therefore, through this webinar, the Center aims to discuss opportunities and the challenges for the SAARC member states, both theoretically and by using the concrete examples from the experience of our panel of experts. In this webinar, we have the honor of having distinguished experts from outside of South Asia. I am delighted to invite Mr. Stefan from the Asian Development Bank, Mr. Johansson from the Research Institute of Sweden, and Mr. Ali from the Steinmüller Babcock Environment, Germany. I am honored to acknowledge the great cooperation and the support extended by all of them for this webinar. This depicts their resolve and commitment to the cause of energy, environment, and to the humanity. In the end, I once again thank you all for joining this webinar and wish you all a very comfortable learning and knowledge sharing in this webinar. Thank you very much and best of luck. Thanks.
Thank you, sir, for your welcome note and for explaining the role of SAARC Energy Center in great detail. Now let's quickly move on to the presentations. Our first expert, Mr. Steve Peters, is a senior energy specialist in waste to energy within the Sustainable Development and Climate Change Department of the Asian Development Bank. Steve has a Bachelor's of Civil and Environmental Engineering degree and a Master's of Engineering Science in Project Management from the University of Melbourne. Steve is a corporate member of the Institution of Engineers Australia and has been a board member of the Australian Chamber of Commerce in Singapore. He is also an executive director of W2E, a biogas developer. Prior to working with Asian Development Bank, Steve was the Group Managing Director of Stratcon Singapore Private Limited and Director of a number of related subsidiaries. He was the founding chairman of the Asia Pacific Biogas Alliance, which is the industry association for Asia's biogas industry. Carrying an immense experience in the field of waste to energy, Steve will help us understand the concepts and technologies of waste to energy systems and will also explain the role of Asian Development Bank in carrying out such projects. So, welcome, Mr. Steve. Can you hear me properly now?
Yes, I can, Umar. Thank you.
Okay, so just give me a second. Let me turn you on.
Okie-dokie.
Okay, Stephen. So I've made you given you presenter rights now. You may share your presentation with us.
Terrific. Okay. Thank you, Dr. Shoaib and Umar from the SAARC Energy Center. It's a great pleasure to be here. I hope that it is a good morning or afternoon, depending on where you are in SAARC. What I'd like to do this morning is do a very basic introduction on what waste to energy actually is and waste to fuels. So Umar, could I just check that my full screen is being seen?
Yeah, I can see your full screen, and you're good to go ahead.
Okay, terrific. Okay, I'll just, I just have to minimize this. Yeah, terrific, done. Okay, so when we talk about waste to energy and waste to fuels, most people think of an incinerator, or they might think of a biomass plant. But in fact, the industry is quite broad and carries a large amount of industries with it. And so what we're looking at is utilizing anything somebody doesn't want. So, excuse me, how am I going to get, yep, got it. So when you look at we're going to look at a few waste to energy projects. We're going to look at a simple biogas project in Cambodia. We're going to have a look at a biomass power plant in Indonesia that actually didn't get built in the end. And we're looking at municipal treatment with biogas, refuse-derived fuel, and an incineration. And we'll have a talk about some energy innovative ideas. The key theme of this is energy transition. So having the ability to take away energy resources from fossil fuels and convert them into things that we can use from our everyday life without the environmental load because of that. So when we talk about energy transition, the common thing that you hear is food versus fuel. The bioenergy dispute in the United States between ethanol production and tortilla manufacture in Mexico was a great example of it. And most people think that's the big argument, but in fact, the argument is a lot more complex. There's an interplay between fuel, chemicals, fertilizer, food, waste, and energy. And inside that process, where you see this multi-pronged arrow, things transfer from being a waste to being a fertilizer, or perhaps being from a waste to being a fuel, or from being food to energy, in the case of biogas. So there are a number of activities where things are interchangeable, and understanding that there is this interchangeable component means that we can then spend time and create wealth by transferring materials from one use to another. So that's how we define waste to energy, getting the optimal use out of materials in your economy. So we'll start off with biogas. Biogas is very, very old. The process is about 120 years old in industrial processes, but as a human function and as a function of animals, it's been going on for a very, very long time. The oxygen atmosphere that we have on the Earth, which is about 19% oxygen, is somewhere around about 600, 700 million years old. Prior to that, we had a very low oxygen content of 2 or 3%. And the bacteria that lived at those times were mostly anaerobic bacteria. That's why many of them are called archaea. So these are the bacteria that naturally occur throughout our nature. So what we're looking at is a very simple process to convert carbohydrates, fats, and proteins by hydrolysis to sugar, fats, fatty acids, and amino acids, all the way down to acetic acid, all the way down to methane and carbon dioxide. So they're not just one bacteria, they're a family of bacteria. And to do it is really quite simple. You need a tank, you need a lid, you need to introduce the effluent, normally at about 8%, so it's very similar to porridge. You then need to agitate it, and I'll get to the agitation component in a minute. And in that process, you will, over a period of time, produce biogas because there are naturally occurring anaerobic bacteria. And the trick with biogas production is to choose the process that you use to accelerate the production of biogas by making methanogens come into contact with food nutrients in a quicker method. And of course, you'll get a slurry out of that, which is a biosolid. So you can get that from food waste, brewery effluent. I was recently in Uttar Pradesh to see a sugar refinery on the back of DCM Shri, a biogas plant on the back of DCM Shriram factory there, ethanol production, sewage sludge plants, Karachi and Pakistan, we're looking at, ADB is looking at doing projects on sewage sludge and cattle effluent in Karachi to create fuel for buses in the Red Line, which we're pitching at the moment. So there's a number of uses for this technology that ADB is employing. One important point is the presence of hydrogen sulfide. Hydrogen sulfide is a very potent poison and has to be removed. It can be removed biologically, but it has implications on equipment when you want to make electricity, or if you're in boilers, it can have an implication on the surfaces of boilers. So these are the sorts of things that you can make biogas from, and biogas can be 30%. Landfills are notorious for having poor production of gas, and the gas varies. You can then make it from factory wastewater. There's a lot of work going on in palm oil mill effluent, cassava, ethanol, food processing, food waste, animal feces, and of course sewage. A key term in the production of biogas is the term COD, chemical oxygen demand, because there's a direct relationship between chemical oxygen demand and the production of biogas. There are some formulas related to what the inhibitory substances that slow it down are, but generally speaking, you know that from a palm oil factory, you might get 65% methane. From a sewage plant, you might get 25%. So it's a very well-defined and well-developed industry. So you'll hear some terms about the different types of bacteria. And if you have a look on the right, you'll actually see a photograph from Argentina, which is actually anaerobes interacting with food. And you'll see that the anaerobes are quite small and they are intrinsically lazy. Anaerobes will only come to eat, will only eat when food is put in front of them. So their life is eat, reproduce, fall asleep, wake up, eat, reproduce, fall asleep, wake up. So it's probably an idealistic existence, but it probably would be a bit dull. The important thing though is that you need to drive nutrients and food to those bacteria, not just the methanogens, in the other processes, the other reactions as well. So mixing and flow rates and turbulence inside a digester is extremely important. You'll hear some terms about the types of digesters. Hydrophilic digesters are normally the covered ponds. They're driven by high water volumes, and they're terrific for tropical areas. In Southeast Asia, they're used extensively. Then you have mesophilic, which is a different type of bacteria mix. They require heating, and then of course there's thermophilic, which occurs above 50 degrees. In China, mesophilic and thermophilic reactors are very common. There are reactors that occur in salt water, and there's an English company that is developing techniques to make biogas on salt water, but it's at this stage not consumer industrial, and certainly not as well developed as the hydrophilic or thermophilic technologies. So I'll just go back to here. So this is a project in Cambodia. This photograph is a photograph of the factory from Google Earth and the facultative ponds where the wastewater was discharged. That's crust. Then there was some process here, and then it would go into some settling ponds. Sorry, my apologies, I've jumped ahead. So what we did was we built a digester that sits pretty much there in that portion, and you can see a photograph of that on the right. That digester is 150 meters long, 100 meters wide, and 10 meters deep, and it has pipe work which you might be able to make out on your screen going in, which is to do with driving nutrients and creating turbulence inside the digester. So the process of making biogas with an in-ground reactor is quite simple. You mix in the wastewater, you mix in any additional nutrients, and in this case there was a root cake that was available from the factory owner, so we could increase the biological load. You put it in a reactor and you create turbulence and you move the materials around so they interact with bacteria. You produce gas. That biogas is wet and has hydrogen sulfide in it. You put it through a condenser, so you dry it out, and then you put it through a H2S scrubber to strip out the H2S, and you can vary the locations of condensate and scrubbing depending on the use and how you configure your plant. There's a thing there called CBG, compressed biogas storage. That is for biogas which has not been which is maybe 60-65%. That can be used for cooking and can be used for some power applications. But a lot of work at the moment is upgrading that gas to make it from 65% to 89%, which for instance would be the SUI gas pipeline standard. 88.9 is the SUI gas pipeline standard in Pakistan. I'm not sure about the pipeline standards in India. So you have a choice of what you can use the gas for, and if you have too much gas, you can flare it. The sludge that you produce needs to be dewatered so that it's usable. It normally comes out at about 3 to 7% solids, depending on how much water you're using, and you want to try and get it to somewhere about 18 to 24% solids so that it can be transportable and usable. And then of course you have some effluent where you might have 5% or 3% of the COD load left in the effluent, which then needs to go off to ponds to be treated. So here's some of the numbers, and there are 3 columns here. One is where the factory was operating at 55% capacity. It couldn't get access to energy because Electricity Vietnam was providing energy from across the border, and with cassava starch, the cassava rots over 3 days. So if you don't have energy for 3 days, you've bought roots and you can't make money. So the factory wasn't making much money. Just at 55% capacity, by providing a stable electricity source, the project added $800,000 to the factory's profitability. And in fact, it allowed them to purchase more roots. And as a result, it basically created $1.3 million worth of additional profits for the factory owner. Now, there are a few points I should note. The emissions component on the just here, emissions of carbon dioxide. At that stage, the price that the project was secured was $14 a tonne. This was in 2008, starting 2009, just before the collapse of the carbon markets. Those prices are no longer available, but still it's a significant increase in profit just for doing biogas. So if you want to have a look at those numbers, I'm sure you will have some questions. And I'm happy to answer some of those questions later on after the presentation. So if you look at the social impacts, farmers don't want to plant a crop that they can't sell. So as a result, because the factory wasn't buying as much root as normal, farmers were planting different crops. When the factory started operating, they started planting more cassava because they knew they could sell it, plus the fact it was a crop that they made money on and it was an easy crop for them to manage. So as a result of the factory being upgraded, not only did the factory owner make money, but local farmers made more money because there was a virtuous cycle of, if the factory is more profitable, then it means that the farmers will get higher prices or be able to sell to the factory because the factory will want to make more money. There was an increased root supply of cassava. That meant more biogas. That meant more electricity, which meant that the factory, again, was more profitable. So it stabilized. The factory at the moment is looking to convert its entire output of native starch to make compostable bags and cutlery. They're in discussion with a Taiwanese group. And this project was very interesting because of the biogas plant, this is now a potential target for a buyout where it can be upgraded to a very clean and green asset. So the factory owner not only got an increased profit, but actually the valuation of the factory went up in terms of what he could actually sell it for. So that deal is in process at the moment. Talk a little bit about thermal technologies. Umar, can I ask, everybody can hear me? Umar? Okay. All right. I assume everyone can hear me. If you can't, could you please ping me back? In terms of thermal technologies, there's a number of commonly used thermal technologies. I haven't put all of them.
Hi, Steve.
Terrific. That's great.
I had muted myself. You're audible, quite audible.
Okay, terrific. That's fine. Just as long as everyone can hear me. It was out there alone. I couldn't hear everybody.
I know, it's fine. Yeah.
Terrific, thank you. So in terms of thermal technologies, there's obviously the classic one, which is incineration, which is thermal oxidation. So basically you're using you're using oxygen to drive and burn a reaction, and you're blowing oxygen in to increase the energy that's there. The other one is pyrolysis, torrefaction, and gasification. We're actually a family of chemical reactions. Now, I know that's not strictly correct, but it in fact is. If you look at it in terms of operation and output, yes, it is correct that they're the similar types of reactions from an operational point of view. So I've grouped them together in the explanation. And then there's, of course, plasma arc gasification, which everybody raves about, and many companies like Siemens have played with, but it is still not a commercially viable technology at this stage, but it may change. So mass burn's very simple. You prepare your feedstock, you put it in the boiler, you have bottom ash that comes out, you have energy in the form of heat, which then can make steam, and then that can be used to make electricity, or the steam can be transferred off for heat use. And then you have entrained gases and entrained particles in the flue gas coming off from the combustion process. They have to be cleaned out, and in some cases you'll have fly ash, which is can in many cases contain toxic materials, and I'll talk a little bit about that in a minute. So it's proven technology. Fixed rate boilers have been used for over 150 years. It's very solid technology. Most of the boilers that are made out of Japan and China are pretty much using a fixed rate mass incineration because it's simple. I know that there are companies doing more advanced gasification, and I'll talk about that in a minute, but generally speaking, this is the least cost, easiest operation to use. Depending on what you have and how your process works, you might have 10% of your mass as ash. You'll have bottom ash, which we were talking about before. That can be used to make bricks. In China, they're making bricks out of it, depending on what is contained in it. And then there's fly ash. Now, fly ash is a real problem for incinerating anything with chlorine, because when you have chlorine in the presence of oxygen between about 250 degrees and 900 degrees, but especially between about 450 degrees and 800 degrees, you make a family of chemicals called dioxins, and you also make furans as well, which are persistent organic pollutants. They're very dangerous. The Americans used that product, one of those chemicals, to defoliate parts of Vietnam. It was known as Agent Orange. But the little known fact is that Agent Orange was first used by the British in Malaya during the Malayan emergency. Not many people actually know that. So when you burn the material, people say, oh, I heat it up to 1,000 degrees and it gets there very quickly. But as the material cools down, you reform those materials. So the process is very important, and the gas scrubbing is tremendously important. So this is a typical waste to energy plant. Sorry, excuse me. This is, you have a hopper, refuse pit, it goes into a grate, it's burnt, then the gas goes through a collection of baffles, through a superheater, economizer, then it's basically stripped out as fly ash. Gas is scrubbed, you might lime dose it, you'll have bag filters, and then it will be released. I was recently at an incinerator in China, and in front of it, they had a very, very large billboard where they were telling in real time what the HCl, dioxin, and other gas pollutants were coming out of the incinerator. And I'll try and share that with the audience at the end of the presentation. But that in China, every incinerator must, in real time, have a billboard in front showing that these are the results, and it must have accredited, that must be certified by a third-party body that the results they're giving are reliable. So yeah, so let's go to, excuse me for a second. I'll get you to, need to get to, I need to get you to this presentation. This is a incinerator in Sweden, outside Helsinki. Please tell me if this is, people can see this.
Yes, it's visible.
Terrific, thanks, Uma.
It's visible, but we can't listen to the audio.
Okay, Well, I can turn the audio off. That's the easiest way to do it then. So this is the basic structure of the plant. It has a large hopper. It treats about 350 tons of waste a day. It's about 140 truckloads. It goes into a hopper. The hopper normally carries 2 or 3 days worth of waste, and the operators use the hopper to a certain degree dry the material out or break the material up. Goes into the chute, and then it goes injected into the boiler, and it's kept on the grate for about 2 seconds. That's typically what happens in an incinerator. That's a good definition of what gets incinerated. So material burns, creates hot gases. You'll see the entrained particles in the gases going through. Now, that is a very, very important slide, and I'm going to stop there because it shows that at the surface of the grate, it might be 1100 degrees Celsius. But by the time it's got to some of the boiler tubes at the top of the stack, it's 900, and as it goes through baffles, it goes to 650, and then 400, and then 220. So basically, by the time the material gets to 220 degrees, it's not really producing that much dioxin. But in this process between the top of the boiler and going through to about halfway through this part of the equipment in ash removal, they are forming dioxins and furans. So that's something that means that you have to have very good quality stripping of flue gas entrainment. So I'll start the video again and we'll go through. So you'll see the gas going through. Fly ash is recovered in different stages of the process. So underneath the grate, you'll have bottom ash, which will fall out, but the fly ash is stripped out through using a number of processes. An electrostatic precipitator, which is pretty much a big mosquito coil. I don't know if any of you have those mosquito zapping machines that are very common. ESP is pretty much the same as that. I know it's oversimplifying it, but that's what it does. Then they use lime dosing. Lime counteracts the acid component of the gases and normalizes the material. And then you have bag filters. Bag filters are very, very important. And inside the bag filter, they'll put a reagent, and that reagent will lock up the materials like furans and dioxins, and then they'll come out. Now, this plant has very high energy efficiency. It's collecting heat and then sending that heat around to the community as district heating. Very, very important process in Northern Europe because obviously heating costs are a tremendous cost. So by the time the gas gets released, it's about 50 degrees Celsius, which is still quite warm, but it meets all the European directives for release of gas. So the issue with incineration is that whilst the process is energy efficient, it's expensive to build an incinerator, but you do have an issue with fly ash, and fly ash is the limiting factor in its success in rollout. So a lot of the work we're doing at the moment is looking at new solutions of how we can deal with fly ash, how we can chemically immobilize it, what we can do in terms of creating ceramics and using hot isostatic presses and other activities. So this talks about the heating and cooling system. So you're basically you're stripping heat out of the gas and using that, and then it goes off to a turbine. And that's producing producing electricity for the local community. But the district heating component of this makes this technology the most attractive. In China, it's very well adopted because of its capacity to provide district heating. One of the projects we're involved in is actually looking at providing district heating and providing options for people currently using coal in the areas around Beijing and Beijing, Tianjin, Hunan area. That's the name of the project, and there's a large amount of investment in terms of getting people to have area heating during the 4 months where it's very, very cold in northern China. This means that they don't burn coal, which means that there are not the levels of pollution that currently occur in Beijing. And certainly Delhi has that problem. I was in Delhi about 4 years ago, and the pollution in Delhi was very, very bad. So perhaps that might be some learning that can get transferred across. So let's go back to the presentation, and I'll restart the slideshow. So we've done that slide. So talking about grates, now this is simplified. I know there'll be people who are experts on grates in the audience who might say that this isn't exactly a good summary, but if you do, I would be delighted to have your comments if you want me to change this presentation internally. But there are different types of grates. There are fixed grates, moving grates, vibrating grates, commonly used in palm oil production for boilers, fluidized bed, and the gasifiers actually use fluidized beds as well. So there's a step between being a boiler and being a gasifier, even in these technologies. And they just, the technology varies in terms of the residency time, the operating temperature, and the combustion dynamics, and they're the determining factors of which technology you might want to use. So a moving grate is pretty simple. It's basically placed on the grate and it burns. That's pretty much it. And the slag, a bottom ash comes off, and you may have some slag depending on what's entrained in the materials. And then you will, if you're doing something simple like wood chips or empty fruit bunch from cassava, or you will then have not a lot of gas treatment because you're not very likely to have the entrained dioxin, the entrained chlorines. But if you go to, this is a bubbling fluidized bed, you'll see that how that process varies. Excuse me, sorry. I'm sorry, we just had a power outage. Can you hear me? Hello?
Yes, I can hear you and I can see the screen as well.
Yeah, we just had a power outage in Manila, so
Oh, it's fine.
yeah, okay.
We at South Asia are also used to these power cuts.
Yeah, I know. But yeah, well, and it was pretty good because the power came back on in literally a quarter of a second, so that was very good. So this is a bubbling fluidized bed. I'll just pop this off to one side. Then you'll have circularized fluidized beds. I'm sorry, the picture's not so particularly good, but you see that there is a process where the air gets basically circulated around in the boiler. Very, in Russia particularly, circulating fluidized beds are very popular in Russia and in parts of Eastern Europe. So key terms, many of you will know these, but I'll just go through them again. Megajoules is a measure of energy, high heating value, lower heating value. How that is determined varies, but nitrogen, obviously it's to a standard, but there is a difference between the high heating value and low heating value of a material. Nitrous oxides, so NO2, NO3, NO4, SO2, SO3, sulfur oxides. CHONS is very important. The relative proportions of carbon, hydrogen, oxygen, nitrogen, and sulfur are a determining component of what particular technology might be better. Heavy metals, everybody talks about them, but in here I've actually specifically spelt out what they are: cadmium, mercury, lead, arsenic, manganese, chromium, cobalt, nickel, copper, zinc, selenium, silver, antimony, and thallium. Now, just as an aside, I was recently in the Marshall Islands looking at a project, and there was a technology that was introduced there to mass burn in the open plastics waste, which was, we gave some very strong commentary about that not being a great idea. When the ash was tested, it had a very high chromium content compared to everything else. That was quite a remarkable outcome, we thought. So dioxins, they're a family of chlorinated compounds formed in the presence of oxygen. They're basically tetrotoxic, so they go into your cells and they vary your DNA. Anyone who's been to Vietnam and seen people who've been severely deformed by dioxin poisoning will tell you that they're pretty awful products. Sensible heat, many people talk about this, but not many people actually know what it means. It is the energy that is required to convert a material from one phase to another. So when you boil your kettle for a quarter of a second or half a second, the temperature will stay the same until it turns to a gas. And the difference of the energy you input for that quarter of a second or half a second is sensible heat. That's very, very important, because when you're dealing with wet waste, and a lot of the waste in South Asia is wet, sensible heat becomes a real problem, because if you build an incinerator, you're basically boiling a lot of water. So it's a waste of energy. Fouling is where you get caked materials that look like they're sandblasted onto the interior of facilities, and that has an implication on the operations and maintenance component. And acid gases are gases formed which basically are quite damaging to internal components, and that's because of the presence of sulfur and other materials. Pyrolysis is a thermal decomposition in the absence or near absence of oxygen, and it produces syngas. Now, I know that India, especially Anchor Scientific, are extremely good at making small gasifiers for agricultural applications like rice husk. They're very popular in Southeast Asia. So this process of gasification in production of syngas is well known. Pyrolysis, you don't make so much syngas, you actually make more bio oil, and you you have tars as well. The next step is to step up to gasification, and that gasification process is the one that's very, very popular in Southeast Asia. Again, it's just a difference in temperature and a slight difference in process, but they're a family of materials. Now, people will tell you, oh, we don't have any oxygen, so we don't create dioxins. That's not entirely true. You can't say that they're not produced, you just say that they're below detectable limits. I think I've seen some documents come out of suppliers in various parts of the world where they say no dioxin is produced. And I think you should be very careful of that, because there's oxygen in the container, in the materials when you start the process. Torrefaction is another portion which occurs at slightly lower temperature. Now, torrefaction is used in Australia extensively to deal with dead animals from a biosecurity point of view. So large chicken farms and large beef farms have a lot of dead animals, and they also have a lot of waste. Now, that waste is obviously a biohazard under Australian law. So what they do is they treat it in a pyrolysis process, and then that is then able to be used as a high surface area biochar, which is very useful for entraining nitrogen fixing bacteria and other things in the soil. So it's sought after by farmers to buy that product. Plasma arc gasification, if we lived in the world of Star Trek, this would be the ultimate technology. It just decomposes everything down to a glass slag and maybe a bit of entrained metals. The only problem is it's about 4.5 to 6 times more expensive than the currently available technologies. And also it's extremely difficult to operate. In the mid-1990s, Siemens had an explosion in East Germany that killed 6 people, 2 of whom were PhDs who were working on the technology. So it was originally developed by the Russians, as my understanding goes. And when you see the space shuttle, that's actually a plasma arc made by Westinghouse, which is injecting a spark to light the bottom of the space shuttle so it can take off. So biomass boilers, this is a project in Indonesia. Oh, sorry. This is an actual factory. You'll see smoke coming out from the factory and also from what looks like a kiln. That's actually burning empty fruit bunch. That was the last month. This photo was taken on the last month that was legal to do in Indonesia. Now it's illegal to burn empty fruit bunch. But if you have a look on the left-hand side, you'll see full fruit bunches, and the purple berries are what are the palm oil fruit. That palm oil fruit is then turned into a number of products, one of which is crude palm oil, and the other one is palm kernel oil, which is the oil inside the shell, inside the berry. And then when you crack that to get the palm kernel oil out, you end up with palm kernel shell, which has basically same properties as coal. So it's commonly used to co-fire in coal. So this is a process from a project in Malaysia, which is on the side of a paper company in Pahang, and they have fuel storage. The most important thing for these technologies to optimize them is the handling and feeding into the boiler. In a large municipal solid waste incinerator, you have a little bit of flexibility about what you can do, but in these processes where you have a fixed biomass, fuel handling is very important to make sure you get optimal results. So it's basically 4 stages. It's fuel handling, steam boiler, steam turbine and generation, and then water treatment within the configuration. So here's some numbers from this project. Again, it was 2008. I can't show you things in the last couple of years because many of them are still subject to confidentiality. I must apologize for that. But 3 mills in this particular area were going to collaborate, and they made about $300,000 a year selling their empty fruit bunch off as a fertilizer, and that was good money to them, and that was shared amongst the people who managed the mill. But if you look at combining the empty fruit bunch from these 3 factories, you could actually generate about 10 megawatts of exportable electricity. And that then means that your operating profits would be about $9 million based on the carbon price at the time. And so maybe 8 million without it. So electricity was in this particular area, there was a shortage of electricity. So the payback was about 3 years. So it was a quite attractive project. A number of these projects were done. This one wasn't done because the 3 mills decided that they couldn't get on and they had a bit of problems communicating with one another, which is a great pity. When we talk about palm oil, I put this in for the edification of my colleagues. If you have a look on the right, you'll see that that's actually peat land that has palm oil planted on it. Peat lands are major sinks for carbon, and anyone who's lived in Singapore or Malaysia has seen the haze caused by burning of these peat lands, and they burn for weeks. That's a really big problem for the palm oil industry, and they haven't managed to create a functional business model to explain how to international donors how that might work. On the other side, there's a lot of people who've been lifted out of poverty from this. About 10 years ago, I remember sitting in the living room of someone in Central Sumatra telling me how 3 of his kids went to university and 4 of them ended up joining the military and getting educations in the military because of his involvement in palm oil. So I think you need to look at the positive and negative sides of it. There's still a big argument about palm oil, but I think it's not so black and white. But as I said, the most important thing is fuel preparation for any thermal technology. If you have a gas fire and pyrolysis, you have very, very tight margins on the fuel on the moisture content. So one of the things I haven't gone into much detail is refuse-derived fuels, but when you have plastics, textiles, timber, rubber, and other combustible materials, commonly they contain a lot of chlorine, specifically textiles and plastics. If you turn those into fuel pellets, you need to combust them in an area where you have controls for dioxin. But one of the other options is to actually stick them in use them in cement production. So sell them off to cement factories, because cement factories commonly burn car tires to generate heat to create the process to make cement. So the RDF component works very well with cement mills without having to build large pieces of infrastructure. Next one is municipal solid waste. This is a different approach to municipal solid waste. This was sort of partially tried in a number of places in India, and I'd be interested to get the feedback from the audience. They had great difficulty operating the digesters because there were obviously some contaminants in the digesters, and also the digester is an agricultural process, it's a biological process. It's not really like a car where you turn the engine on and the car runs. Sometimes the gas is produced, sometimes it's not produced as much. So there's it's a bit more like managing cattle than actually driving a car. So to manage this process, you need a little bit of subtlety and a bit of patience. But effectively, you take waste, you strip what you can out of it, you shred it, you pulp it, or you can put it through a trommel screen. But ultimately, what you want to end up with is an entrained amount of organics that go into a digester with as little plastic and as little contaminants as possible. And then the process is very similar to what we talked about in the cassava factory, probably a little bit, the few more controls. But then you have a market for the recyclables. So it's a choice between building a large incinerator or building a smaller biogas composting type approach. And many countries, especially India at the moment, and it's because of the closer relationship with China, are actually building incinerators to change the way people collect and run waste. And we're seeing these types of projects come in, and we're not sure how that's going to work in India because South Asia obviously has some very clear supply chains for the collection and handling of waste, and so we're still in our working out how that will deliver. This is the sorts of agreements that you would need if you were looking to do an RDF type project. This is for a project in Accra in Ghana, and this also obviously is not ADB. This is from previous company I worked with, and you'll see that there's a lot of agreements and a lot of documentation that you need to have. So this makes these waste to energy projects quite complicated, and getting agreement and also the cost for doing the pre-construction work is significant. It's rarely under 200,000 US dollars and is commonly $500,000 to $2 or $3 million in terms of legal fees, in terms of setting up people to do on the ground studies, pre-design, environmental impact studies, all these sorts of things. So it's not an easy technology, and it's not an easy business to be in. It's a very important business, but it's not got the level of attention from the international community that perhaps it should have. So in Ghana, they couldn't afford to build a large incinerator, but they could get access to about $56 million worth of capital cost. And so this project had an IRR somewhere around about 14 or 16%, which is not great, but it certainly passes hurdle for economic analysis. So I'd like to show you another video now, which talks about, I mentioned a trommel screen before. I'd just like you to, let me just shut that one down, and I'll show you another one, which is a trommel screen. So this is an American company called Harden. So they're shredding and then they're running through a trommel screen, and then they're hardening. So this tube with the rotating tube is a trommel screen. So it has holes in it, so to strip out the smaller organics. Then the larger organics go on a conveyor belt, then they go into a shredder. So anything the size of a small Yakult bottle will already have come out, and then it goes into a shredder. That's not a place to fall into. Certainly a very, very dangerous piece of equipment. Then that gets chopped up to a smaller size. They may even chop it up further. And then they have a number of choices. In this particular video, you'll see that they're actually, this is a landfill that they've dug up, and then they're taking this material and then they're baling it to turn into meter by meter bales. So you'll see them baling it here, and then that gets shipped off to be incinerated. And I'm not sure what the use of that is. It may be an incinerator, it may well be or a cement factory, but that is a common process. Notice the guy's wearing a lot of PPE. He's wearing safety equipment because there's a lot of material in there that's perhaps not so great to inhale. Okay, so then I'll show you another one, which is instead of doing a small bale, you do a pellet. So instead of doing a meter by meter bale, you do a pellet. This is a machine in Thailand. So all it is a rotating die, and it just makes a circular pellet, and you'll see the entrained solids and the plastics in there. That makes that's a very small machine, and it makes about 100 kilos of pellets an hour. So that is used for shipping. It's a lot easier to ship that in bags than to run the bales. Plus the fact that bags don't leak as much, and they sometimes use cassava starch just to bind those pellets together. So they'll mix in some cassava starch so that they have a discrete form. That pellet is a lot easier to burn because it's more consistent. So that's another type of technology, and I'm going to turn that off, and I will go back to our presentation. And what I wanted to talk very briefly about was just some planning. So you talk about Phnom Penh is experiencing phenomenal growth. Phnom Penh is the capital of Cambodia. 2015, there were basically 2,300 tons of waste a day. By 2025, they think it'll be more than double that at 5,000. So they currently have a dump site at Stung Mung Che, which is closed, and that's right on the edge of the very densely populated Dawn Peng, Yuchong, Makara, Jamkar Mon area. And what they decided to do with the help of the World Bank was to build a landfill at Dang Khao, which is further out of town, which is actually very close to the killing fields, if any of you have been to Cambodia. Sorry, I'll go back. So Dang Khao is now almost fully used. It's very unlikely that it will be able to be used in the 2020s. So they need a new solution, and they need a new solution quickly. And a number of organizations have looked at planning this. So they need some new infrastructure. They need to have about 40% of their capacity as an incinerator / biogas plant. And the plan was to put that in a place called Snar I have to say, it's very difficult to speak Khmer, but Snarl is outside of town. Whilst it is not particularly population dense, it will be by the 2030s, 2040s. But they'll also need to have a RDF station and a biogas plant near Riverside, near the ports, because they just won't be able to take all of that material out during the full day. So we suggested to them that they'd do an incinerator, but not an incinerator to 5,000 tonnes, but a 2,000 tonne incinerator, and then spread treatment out across the rest of the area to allow people to make money out of plastics, to make money out of biogas and other technologies. Building a 5,000 tonne incinerator means that you have trucks bringing 5,000 tonnes a day of waste into one area. That centralized model doesn't particularly work well at that scale, because it means there's a lot of rubbish trucks on the road, and it has health implications. So if we talk about the type of projects that ADB is working on, you can see that there's municipal solid waste, biogas, solid fuel, biofertilizer, and biomass. Now, anything that's underlined, ADB has done. Anything that's in red, ADB is not going to do. If you look at the things in black, they are the technologies that really are the strong thermal technologies. And incinerators are popular. They've done one gasifier in China. I don't know if they'll do another gasifier. There was some review of plasma, but plasma was not done by the bank. And thermal depolymerization, which is a technology out of the United States, which I strongly recommend you look up on the internet, has not been done. But then if you look at the portfolio again, there's waste heat recovery. So there's taking gas turbines and doing the waste heat recovery from those to get more energy out. Organic Rankine cycle turbines, where you're looking at recovering heat from a process and turning that to electricity. Preheat and process heat shifting, heat pumps. Those are all things that the bank has done. It hasn't done much on nano antennas or biotechnology or MSW to chemicals, but MSW to chemicals will probably be in our project mix within 2 years. Dimethyl ether, which is ester, which is a fuel substitute, and that's being looked at in China, and bio-CNG is being looked at in Pakistan for the red line. But the rest of these types of technologies in biofuels and alternative fuels haven't been looked at. So that's the sort of scope we're looking at in waste to energy. We have some projects in the Maldives. I think there's a waste to energy project in the Maldives. There's work in Bangladesh, and there's also work in India on waste to energy as well. So I wanted to talk a little bit about innovation. This is a project in Sweden, which is a biorefinery. So they're taking materials, turning them into gas, and then they're stripping that gas, the CO2 from that gas, to make liquefied natural gas to be shipped, and also compressed natural gas to run cars. And that makes sense. That makes financial sense in Sweden. Now, obviously, that's not going to make financial sense in countries without a CNG industry. But if you look at the penetration of CNG in Pakistan, you would wondering why Pakistan is not doing more of this type of work. And that's some of the things that we're trying to look at and assist people to show, demonstrate those projects, so people can then get the confidence to do them. There's a really wonderful group of projects going on in Rotterdam at the moment. And in fact, there are 2 organizations, but this is the biggest one, Enerchem, which is a Canadian company. It is looking at taking waste and converting it into methanol and some base level plastics. And so this project has $1 billion worth of investment, and it has Air Liquide, AkzoNobel as shareholders. So it's a very, very large project. That project is going to, I think, in 5 to 10 years, become a very common way for people to treat plastics and other materials that can be used to recycle and recover plastics so that they're used again. Because we have a very large backlog supply of plastics that currently are ending up in the oceans, and we can look at making money out of those and investing and making returns. And this is more than likely to occur in free trade zones and around ports. This is what our expectation is in terms of how that development might go forward. We don't think that this will be done at small city level. We don't think it'll be done by municipal authorities. We think it'll be done by multinationals working out of these free trade zones. That's a process that I would suggest that you keep your ears and eyes open for. So building a very, very large incinerator then means that these type of projects can't get up or can't get access to materials. So that's why we're suggesting that don't build a very large incinerator, just build an incinerator for the things that you absolutely have to incinerate. Another one is a project in Copenhagen. It's currently being built, and that's the waste to energy plant in the background, and that's a ski slope. And yes, they are skiing down there, and it's summer. And the reason they're doing that is they're taking the heat and they're turning into cooling, and they're then making the waste to energy area a public space. So that's actually an artist's model of what it will look like. And they're about halfway up the building in terms of construction. I would again suggest that you look at the press releases on that particular project. Waste to energy is a great industrial technology, but also it's got the opportunity to create, it has the ability to create opportunities in the urban, changing the urban landscape. So I don't know if anyone has been to Hokkaido, to Sapporo and Hokkaido, where they turned a landfill into a public park very, very successfully and integrated waste management into that, so that it actually became an education tool. Now, I know that might sound difficult for places where there are limited resources and limited budgets around to do waste to energy, but it's something that might catalyze your thinking, and there might be a localized solution that might be appropriate. So I'd ask you to keep your mind open to that. So on that note, I'd like to thank you for your time. I'm sorry if I've gone over on the presentation, and I'm very happy to take your questions. Thank you very much.
Thank you very much, Steve, for your very detailed presentation, and it was very comprehensive. You comprehensively covered aspects such as methane exit sources, bacterial reaction, CGAR, biogas technology, municipal solid waste, etc. So we have a lot of questions here. So I'll quickly go through the question and answer session, you're requested to keep the answers short and precise, so that we can close this session quickly. So the first question is from Mr. Shakil from Pakistan. He says, can you explain more on ADB's work regarding use of biogas as transport fuel in Pakistan or other countries?
Okay, so if you look at Karachi specifically, if you go for a ride on Karachi Bay, you see gas bubbling up from the bottom of the bay because so much biosolid ends up in the bay, whether it's through drains and it's cattle from Landy or from Baines Colony, that this biosolid ends up in the bay. So if you look at the capacity within Karachi, Karachi has a phenomenal capacity to make biogas, but it's not making it. And it can make it from sewage sludge, it can make it from cattle effluent, it can make it from food waste. So you could theoretically power most of the buses in Karachi using compressed natural gas. But to make compressed natural gas, you need to make biogas, which might be, say, 60% methane or 50% methane, maybe 30% carbon dioxide, and then maybe 5% or 3% trace gases. So you basically remove the CO2. And you do that with a number of ways. You can use a membrane, you can use some other technologies. I'm happy to share some information on that subsequently with Umar, and he can share it with you. So then if you have 100 cubic meters of biogas, you end up with about 650 cubic meters of compressed natural gas, which will be 90% or 89% methane. And then the rest will be some CO2 and some trace gases. So that is the important part. It's called gas sweetening or gas upgrading, where you strip off the CO2 from biogas to make it to the equivalent of natural gas, and that is called biomethane or bio-CNG. Okay, Umar, right. Next one.
Yeah, so we have another question from Mr. Nawaz Ahmed. He asks, what is the estimated CH4 or methane that can be recovered from 1 ton of municipal solid waste? Do you have any numbers?
Well, that depends on the feedstock. So there's a wonderful book called the Biogas Handbook, which will tell you give you those numbers in a table. But again, if you use the numbers from the biogas handbook, you might be wrong, because the process, for instance, cassava starch uses a lot of sulfur in its process. So you'll get a number in the biogas handbook assuming a certain amount of sulfur is used. But if they use more or they use less, the number will be different. So to put it in perspective, the worst things to make biogas from are coffee grounds. They're the lowest, and probably palm oil mill effluent and empty fruit bunch have the highest yields. And probably the most difficult one to make biogas from is effluent from ethanol production and the back of sugar refineries. So I can share with you the product on where to find that information.
All right. We have another question. Is fly ash? This question is from Mr. Ashta Bhatia. He asks, is fly ash or bottom ash saleable in the market?
The market would say yes. I would say no. I am currently working on a project to look at an alternate technology for locking up fly ash. It can be used in cement, but then when you have to demolish the cement, the building that's made of that cement, you will release some of these materials out again. So it's still going to end up in the ocean. We need to have a solution which is inoculates this material over geological timeframes, and we're working on trying to do that at the moment. We're trying to do that on one project at the moment. So I don't believe that it is a commercially viable solution.
Okay, thank you. There's another question. To what extent is it commercially viable to use biogas as pipeline gas in South Asia?
I think highly. I think it's well, a month ago I was talking to Sui Southern Gas about exactly that. And in fact, Sui Southern Gas Sui Gas is the pipeline gas in Pakistan. I'm sorry for the other members of SARC who I should have said that. Sui Gas is the pipeline that runs from the Sui gas fields in Pakistan and has been used all throughout Pakistan. We spoke to them. They were very open to looking at commercial transactions about how we might manage the intermittent production of gas versus the constant need for the buses, and how we might create they were very interested in, and they knew what they were talking about. So yeah, I think there's a possibility for it. I think certainly in India, it would be a wonderful thing to look at doing in India, but the challenge in India is getting permitting done and dealing with people who are going to look at pressure groups and the social side of it. So I would be suggesting that the challenge for this is not commercial or technical, but it's social.
All right. And there's one more question. What is the estimated payback period for waste incineration techniques, considering all the incentives available in South Asia, or particularly in India?
Yeah, particularly in India is actually the color of that comment. There is a new policy that's released by the Modi government, which is very, very pro centralized collection and has basically facilitated a number of projects being looked at in waste to energy in South India. In India. I don't know the exact details yet. I'm still in the middle of a project where we're looking at that. I'm waiting for a report from a set of consultants. I probably will have an answer for that in 2 or 3 months. But what I would say though is that whilst there are policies and there are very proactive policies in India, they're new policies and they haven't been tested in the courts and they haven't been tested through implementation. So there's a significant risk for people entering a very new market, especially because you have entrenched interests in that market. You know, the people who are collecting waste and the supply chain for that. So yeah,
all right.
That's my opinion.
Mr. Ashta Bhatia asks, what is torrefication, which you mentioned in the presentation?
Okay, so when you char something and you make charcoal, you basically flash off the water and then you carbonize the material. If you go a little bit further and you change the structure chemically a little bit further, that becomes torrefaction. It's the step before pyrolysis. So it's a type of chemical reaction. The beauty of that chemical reaction is that it can occur quickly and it can create a high surface area material. So it can be used if you have a substrate which is not terribly biologically compromised, you could use it as a water filter, but if it is, you could basically inoculate those materials with heat and then use it as a fertilizer or as a soil augmenter. It increases the surface area of soil, and as a consequence, it means that you have more nitrogen-fixing bacteria and other bacteria that can actually replenish the nutrients in the soil from the atmosphere.
All right. There is a question from Nimal Pereira. Will there be a particular role or initiative offered from ADB if waste to energy projects are initiated in Sri Lanka?
How to answer that question? The short answer is I should explain the way the bank works. The bank has a sovereign operation where we lend money to governments, and the governments ask us to help them. We tell them what we think they can do, and then we work out a strategy and a plan with them. That's about 60% of our lending. The other part of our lending is where we lend to emerging corporates, who are companies that are doing things that are important for the development of economies and alleviation of poverty. And so we are looking at projects in Sri Lanka. I can't tell you what they are, but yes, we are. And we are looking at corporates who can deliver those projects. That's all I can say. I'm sorry, I can't say more. But if you have a project that you think might work, and you have a government behind it, or you have a shareholder with a balance sheet that's strong enough to deliver the project, then yes, ADB would talk to you. But if you're just a person with an idea, I would recommend too that you try and work with someone who can deliver the project, because I don't think you'll get very far in our processes if you don't have the financial resources to get the project done.
All right, so basically we have a lot of more questions, like I have a list of 8-9 more questions with me, but if you could wait for like till the end of the session, and we could then ask those questions towards the end, and I just want to ask your availability if you're available.
Yeah, I am, Umar. Could I ask a great favor? Could you email me those questions?
Sure, that would be
yeah.
be
How much do you mind offload? That's next session is probably going to be about half an hour, yeah?
It's going to be shorter. It's around 20 minutes long.
Okay, all right. Because I may have to duck.
Sorry,
Yeah,
let me just confirm from my next panelist if he's ready. If he's not, then we will continue with the question and answers.
Sure, no problem.
So, Mr. Johansson, can you hear me?
Yes, I hear you well.
All right, so we will cut short the question and answer session here with Mr. Peters, and we have a lot of questions. We would either take him towards the end or close of webinar, or we would email the questions to Mr. Peters, and he would be glad to reply to the questions individually. So moving on, our next presenter is Mr. Inge Johansson. He has worked as a researcher in RISE Research Institutes of Sweden for the last 6 years. During his time, his main focus has been waste to energy, even though he has also been involved in waste mapping, material recycling, emissions, and other projects. He has a lot of focus on what's going into the waste to energy plants, as well as the residues which are leaving the plants. His area of focus is His area of focus is the industry and developing practical applications for them. Internationally, Mr. Johansson is a member of ISWA's Working Group of Energy Recovery. He is also the task leader of IEA Bioenergy Task 36, which is integrating energy recovery into the waste management system, and a convener of ISO TC 300 solid recovered fuels. Nationally, Mr. Johansson is also the coordinator of a strategic network called Waste Refinery. Prior to RISE, he worked at the Swedish Waste Management Association as a technical advisor on energy recovery, during which he worked with all aspects such as policy, legislation, education, technology, and also a lot of coordinating working groups within that association. I apologize, Mr. Johansson, for the delay. You will be giving presentation on waste to energy opportunities and challenges from a Swedish perspective. So, Mr. Johansson, you may proceed.
Thank you. It's a pleasure to be here and to give a speech about the perspectives we see or the experience we have in Sweden. I apologize a bit if my voice will crackle down. I'm suffering a bit from a sore throat, so if I start coughing a bit, it's not intentional. I also want to thank you, the previous speaker, for giving a good background on it, and that will help my presentation as well, or the understanding of it, I hope. I will just start about mentioning some few words about IEA Bioenergy, as well as my company RISE. So IEA Bioenergy, the technical collaboration platform, it has a similar scope, or rather the IEA has a similar scope as your organization, and the bioenergy platform is a freestanding platform under the umbrella of IEA, and the mission is to look at and increase the knowledge and understanding of bioenergy systems, and by doing that also facilitate commercialization and market deployment. And we have like 10 different tasks or working groups within the technology collaboration platform, which works on information exchange a lot, doing policy, technology, research and development. They're also doing quite a number of projects in different areas, and we are covering like combustion or co-combustion. We are covering liquefaction, more or less pyrolysis, gasification, biogas, conversion into fuels, liquid fuels, biorefineries, supply chain management, sustainability. So there are a number of aspects covered in the work being done. And currently there are 20 IEA members, and also 3 partner countries, and the intergovernmental participation is from the European Union, or the Commission of the European Union. So task 6 that I'm the leader of, we are looking at integration of energy recovery into solid waste management. We are also moving a bit more towards the role of waste to energy in the circular economy, hopefully for the next triennium. The work is done mainly by we're having 2 meetings each year, associated with workshops and together with technical visits. We're also doing some smaller studies or case studies that we publish as task reports, and those are or will be available at our webpage. I've given 3 examples here just to give you an example of what it could be. The current members are France, Germany, Italy, and Sweden. So it's very European right now. For the next triennium, we hope to get in Australia, US, and maybe Canada. And we are looking for more members. So at the last EXCO meeting, actually India participated, and we are hoping that India will join IEA Bioenergy, and I personally hope then that they also would like to join the task 36, looking at waste to energy and waste management. RISE, which is my employer, it's Research Institutes of Sweden. We are fully owned by the government of Sweden. We are a research institute, a polytechnical one, and the largest one in Sweden. And we are to fill the link or be the link between academia or the universities and the industry. Traditionally, the university has made a lot of fundamental research funded by the government, while the institutes have been more applied. And now those borders are a bit blurred, because now universities are more dependent on external funding as well. So they are tending to go more towards applied research as well. But we are still working a lot together with universities as well as the industry. We are around 2,300 people, and 1/3 approximately has a PhD degree in that. And we also have quite a lot of facilities for testing and demonstrating the different aspects or different technologies. We are working in a lot of areas, so this is just to give you an example, and you will get the presentation afterwards, so I won't go into the details, but we're working with anything from life science to energy to vehicles and vehicle safety and concrete, glass, wood, most of the different materials that are around, graphene and other things. Waste refinery was mentioned before, and that's one example where we are working together with the academia and the industry. So it's today it's a strategic network. It has been a researching network as well. It's cooperation between academia, universities, institutes, society, and industries. In this case, society is some municipalities and waste management branches or administrations of the municipalities. We are working together in common projects, and we are trying to develop common projects where we partly get financing from our partners in the network, but normally applying for publicly funded research projects as well. We're doing a lot of networks we have a network there where we can also get answers in a quite efficient manner just by putting out a question, and there are a lot of competencies that can easily answer to shorter, simpler questions. We are doing some seminars, and we are kind of having the industry in this case as test beds where we can do trials in full scale in waste to energy plants, for example. So that's just a brief overview of the background or my background. I usually, when speaking about waste to energy, I usually start with this picture. You will just in a minute understand why. I usually ask people what does these cars have in common? Well, actually, they are both Fords. They have four wheels and an internal combustion engine, but more or less that's where the similarities stop. And they have about as much in common as these. So the top left one is the first waste to energy plant in Sweden. It's outside the capital of Stockholm in 1907, or taken into operation 1907. There was actually waste to energy in that site until 1986. Then in updated technology-wise and also expanded capacity-wise. The lower right is a plant in the southern of Sweden, in the third largest city, that was built in, it was built in two steps. It has been into operation from the 70s, but these two lines were built in 2004 and 2008. Being state of the art, and from the first one, not having any emission reduction, not recovering any energy. The last one are providing 60% of the district heating in the city, also having the state of the art emission abatement systems. Sweden is not that a large country, so I thought I would just point out on the Google map where we are. We are often confused with the country Switzerland in Central Europe, but we are located in the northern part of Europe. We are quite a longer country, and we are not that many inhabitants. We are around 10 million in total, with the largest city of Stockholm being the surrounding around it being a bit more than 1 million people. If we look at the waste situation in Sweden, we have one major contributor, and that's the mining industry. Mining is a very large industry in Sweden, and they generate a lot of waste. However, I won't go into that because the waste to energy in that is not that interesting. I will focus more on the municipal solid waste and some of the industrial and construction demolition waste. So if we look at the municipal solid waste in Sweden, it's around 4.5 million tons a year. So it's around half a ton per capita each year. If we looked at the treatment today, we say that more or less 100% of the waste is collected. Some of the waste is of course dumped some places, but it's not a very large problem in Sweden generally. There are well-functioning services for the collection of the waste. So we are around 50% going in material recycling and biological treatment. That's not the same as 50% being material recycled, but that's what's collected for material recycling and biological treatment. Then we have approximately 50% going to waste to energy. In the biological treatment, you also have some waste to energy because you will have anaerobic digestion in that. But since we are recovering nutrients, that's in statistics, that's pointed out as material recycling and not waste to energy or energy recovery in itself. Development of waste to energy in Sweden from the first plant, we had there had been, especially in the 60s and 70s, development on starting to building plants. And in the middle of the 80s, we have a moratorium for building new plants because then we had an alarm about the dioxins that the previous speaker mentioned or spoke about. At that time, the Swedish waste to energy plants were emitting around 100 grams of dioxins into the air each year. So there was a stop to building new ones in the middle of the 80s. But after discussions with the authorities about what needed to be done, what investments and flue gas abatement technologies that needed to be installed, that was lifted. However, the really large changes we started to see around 2000, because then we introduced the landfill tax. That landfill tax today is approximately 45 euros per ton. Also in 2002 and 2005, we introduced landfill bans on combustible waste and organic waste, which also put a lot of pressure on the rest of the waste management system. So then we developed a lot of waste to energy plants, especially on the industrial and commercial waste. As you can see, the upper line is the total amount of waste to energy, and then we are speaking about waste incineration, more or less. And the lower line is the municipal solid waste. So the amount of municipal solid waste that has gone to waste to energy has not increased nearly as rapidly as the industrial waste. And that's one of the factors of that is economy, because the municipal solid waste municipalities have they're responsible for, and also they will have the funds for it because they will take a fee from the inhabitants or the public for it. They are not allowed to take profit on it, but they are allowed to cover that costs. So they can choose environmental more beneficial option and then put that fee on the inhabitants. So in total, we have somewhere around 6 million. I think that the capacity actually is closer to 7 million tons of waste a year going to waste to energy. And this figure also shows that's the gray bars is the existing capacity. Then you have blue, that's plants with environmental permits. The dark gray is under contract or commissioning, and then you have some plants as well without environmental permits. The line with the dots is actually the residual waste available in Sweden after material recycling. that also includes like rejects from material recycling in it. So for a long time there was more waste than we had capacity, but in the economic crisis in 2008, that changed. So we saw decreased amounts of waste being generated, and as well as at the same time as the capacity was expanded quite a lot. So now we are, the Swedish plants, as they say, are offering a treatment service to the rest of Europe. It's mainly Norway and the UK currently, but there have also been other countries delivering waste to Sweden. And in this case, the plants are not buying waste, or they are buying waste to a negative price, so they are taking a gate fee to receive the waste. One driver of this has also been legislation in other countries like the UK, where they introduced a landfill tax a few years ago, which they ramped up to around it's above 80 pounds per ton, British pounds, which is massive, and that has had a huge impact both on the development of waste to energy within the UK, but also waste streams seeking alternative treatments outside the UK. Both the Netherlands, Germany, Sweden, Denmark, and Norway are taking waste from the UK. So what are we doing with waste? What are we recovering? In this figure, actually, I've included both waste incineration as well as biogas. As mentioned in the Finnish case, we have the same in Sweden. We do have district heating. So heat is a very sought after product and with a quite high value. So most of the energy recovered is in the form of heat. We also generate electricity. So we are generating a bit more than 15 terawatt hours of heat each year. It's also going to industries. Like there is an ethanol plant being provided heat from a waste combustion facility. There is also a paper mill being provided heat from a facility, waste energy facility. And when we look at the biogas, we are mainly using converting it into vehicle gas, because that way we will replace fossil fuels directly. When we are using it as heating and powering, it's competing with biomass, water power, and other renewable sources. So the benefit from an environmental point of view have been great on vehicle gas. Looking at some of the success factors, well, I already mentioned one, the district heating. We had, if we go back to the 1940s, everyone fired their own stoves, which produced a lot of smoke, produced a lot of particles. Some municipalities started then to introduce the district heating networks, where you generate the hot water in a central place and distributing it to the homes. This is a very good option for waste to energy, because if you look at waste incineration, it's extremely suitable for generating heat. You have more technical difficulties generating power with high efficiency. You will have the same technical difficulties or similar technical difficulties generating high amount of electricity from gasification as well, I would say. So that has been a large, you had a need for heat, and that need has driven the provision of economically compatible fuels, which right now waste is one of the most economically feasible fuels in Sweden. Another point is actually trust. The plants have been quite open. If they have a problem, they have been open with it. They haven't tried to hide them. But also you have a large trust in the authorities from the public. And the authorities has not really given the public any reason to doubt them very much. Of course, sometimes decisions goes wrong, but in a majority of the cases, they are making good decisions, even if you might not like them all the time, neither as a private person or as a company. Cooperation has been a very important factor. The companies have been established by municipalities in most cases to begin with. Now there are a number of private actors as well. Since there was more waste than the capacity, they had not been competing about waste, so they realized that, well, if you have a general problem for waste incineration, we all benefits to solve it together. Like it was the case when looking at dioxin. I think the Swedish industry have been the largest funder of dioxin research from waste to energy, probably in the world. In general, they are doing a lot of networking, and they're even exchanging spare parts. If a plant breaks down, they call another plant they know have the same equipment, and they are lending that spare parts in wait for, and then order a new one that they can give to the other one. And I know that I was in a conference in the US where I was at the table with boiler manufacturers, and they said that, well, the Scandinavian market is quite special because you can't really hide when you have made an error, because even if you try, the rest of Scandinavia knows it by the day after anyway, because the plant owners communicate. If there's a problem, they communicate with each other to try to avoid it being duplicated in other companies. Education is another matter. All the plants are inviting the public to visit them. They will usually have 1 or 2 days a year they are open for public, but they also accept technical visits from the public, as well as organizations, international dignitaries, and schools. They are having a lot of school kids there. They're also creating learning centers in many places where they educate the kids about waste management in general and the role of energy from waste in that waste management. Our previous speaker also mentioned something. It would come back here. Looks do matter, even if they say that it's the inside that's the important thing. Looks do matter, and it's a trend we see.
Excuse me, Mr. Johansson.
Yep.
Yeah. So our next presenter, he's in a bit of a hurry. He has to attend a meeting. So he was requesting if you could finish your presentation in like 10 minutes, so that then he could go on and deliver his presentation.
Yep, that's no problem.
All right. Thank you very much.
So in the upper left corner, you have the Spittelau plant in Vienna. That was designed by the famous artist Hundertwasser. That has become a tourist attraction, more or less. They have a subway station right beside it, and there are a lot of tourists taking selfies beside the plant. It might not be something everyone likes, but it has made it a natural part of the city. To the right, it's the ECN plant in Paris. It's located in a business area with a lot of offices. They have dug it down like 34 meters into the ground to keep to the height with the surrounding buildings. It's not the typical facade as well from an industrial point of view. And then in the lower part, you have the Copenhagen plant that was already mentioned. Actually, the plant is up and running since a year. The ski slope and the park on the top of the ski slope is not. It will be commissioned. I think they were saying something that it should be finished by October or something. I visited the plant in May. It will be accessible by the public. Actually, the actual ski slope will be plastic material, so it will not be actual snow. But the municipalities that own the plant put the demand on them that's saying that they need to make something available for the public. A certain percentage of the area they took for the building should be available for the public. The plant also is situated like 3 kilometers from the city of Copenhagen, which is the capital of Denmark. It's approximately 3 kilometers as well from the Royal Palace. So looks and the integration with the public sphere is an important factor. If I leave the opportunities and go a bit to the challenges that we see now, and also some of them that we have tackled before. One upcoming challenge is what's the role of waste to energy in the circular economy? And also our previous speaker mentioned that you might not want to put all your eggs in one basket and just make a huge incinerating, taking all waste. That's not really the way to go. But what will the place be in the circular economy and in the transition to the circular economy? And I think that in the transition to circular economy, we will see an increase, especially in developing countries, for the waste to energy. That's to destroy a lot of material that contains unwanted substances and hazardous compounds, and to concentrate those into ashes to manage in a good way. We also have a lot of carbon death or substances that are built into like buildings with a lifespan that's fairly long. So we will see some of these for a long time yet, even if we are transitioning towards a circular economy. One aspect that's at least have become quite large in Sweden now is that the municipalities and as well as the government are adopting a vision of being having a fossil-free energy system and both energy and transport system. And then you have the problem how to tackle the plastic going into the waste to energy plants. There are definitely plastics today that neither the material companies nor the authorities want to recirculate into the technosphere, because they can contain flame retardants and they can contain PCB and other non-desirable substances. And I guess we will see here if like the Enerchem solution or other feedstock recycling options with gasification or other thermal cracking of chemistries or biological for that matter can be a solution to that. Residues and ashes was one area already mentioned as well by previous speaker. That is a challenge. In many countries in Europe, the bottom ash or the slag is used in construction purposes for roads and parking lots and other things. In Sweden today, not so much. It's used as construction material on landfills, but you have not succeeded in getting the acceptance to use it in roads. There have been some being done on it, but not widely used today. And that's also a bit for the legislation and policy parts. What we do see is an increased interest in looking into actually recovering metals, and in Switzerland I have a plant producing pure zinc from the fly ash, and looking at that as an urban mine. That would probably be something that might come along more. Legislation is a challenge. It can also be an opportunity, like in the case of UK when they put in the landfill tax. Another case is for biogas, for example. In Sweden, the government has decided to stimulate the use of biogas through having an exemption on CO2 tax as well as energy tax on it, making the consumption of it cheaper. While in our neighboring country, Denmark, they have put a production support in place where they get an incentive per cubic meter of gas they produce or megawatt hour of gas they produce. The problem is that when the Danish export their gas to Sweden, they get both incentives. So they get both the production support as well as the tax exemption. Legislation and incentives are important, but it's also important to coordinate them between. So just to wrap it up, waste to energy can contribute to a better waste management and provide a path to renewable energy, but it's a part of a solution, not the solution in itself. It needs to be incorporated in with other waste management solutions. In Sweden, we have worked a lot with source separation to get pure streams, especially for the food waste going, if we want a fertilizer that's of good quality. That has been one option. We have worked a lot with cooperation between the plants and companies to learn from each other and others. An openness towards the public, and also to not deny problems, because they will up to the surface, especially today where the information technology is so available, and scandal will not only face one plant, it will face the whole business or the industry. You might need a political will, or at least not that they are against the solutions. You need to have the legislative framework to be in place to be able to do it, especially on waste management, but also the integration of waste management into the energy system. And do not compromise on safety or emissions, because then you can kill the whole future for waste to energy in the business. So that was my presentation, and yeah, I thank you all for listening.
Thank you very much, Mr. Johansson, for your wonderful presentation. My apologies, we are running behind our schedule, so that's why we have to keep a few presenters waiting, and we have to cut short your presentation. We have a few questions from your presentation. I hope you will stick around so that we could ask the questions from you towards the end of the session. Now moving on. We have Mr. Ali Disbe with us. I hope, Mr. Ali, can you listen to us? Hello, Mr. Ali. So I think Mr. Ali is facing some technical problem while connecting with the webinar. Meanwhile, we could
Sorry, yes, now can you hear me?
Okay, Mr. Ali, welcome to the webinar.
Yes. Can you hear me now?
Yeah, I can hear you.
Perfect.
Let me tell our audience that Mr. Ali is the Area Sales Director for Waste to Energy Business for Business Area in India and South Europe for Steinmüller Babcock Environment. He is an engineer and working in the waste to energy business and air pollution control system since many years. Mr. Disbe will be giving a presentation on waste to energy systems with great firing. So, Mr. Ali, I'm giving you the presenter rights. You may share the screen with us. Yeah, we can look at your screen now.
Okay, good morning, everybody. Now, I will try to start my presentation. Can you see it?
Yeah, we can look at your presentation.
Okay, perfect.
Many apologies for the delay.
Okay. Now, good morning, everybody again. The speaker before me has explained very detailed about the waste management system in general. It was very informative for me too. Thank you very much for that. Now I will try to explain you now a part of this waste management system. It is how we can treat the municipal waste, in which way we can reduce the volume. Okay, we are doing by means of installation system. Of course, in Scandinavia, we have also installed a lot of plants. It is most probably by Mr. Johansson is well known, our process and technology. Now, but before that, I will introduce very short our company. I am from the Steinmüller Babcock Environment. We are designing environmental and energy technology plants. We are erecting two, and we have experiences more than 150 years in this business area. In environmental and energy technology area, we have for the both systems worldwide 1,600 references worldwide. And we are a member of the Nippon Steel group, Japanese group, since 2014. The roots of the company go back to the 19th century. 1874 and 1898, two famous company established with the name Steinmüller and Deutsche Babcock in Germany at that time for the producing of the energy from coal. And over the years, they have developed the systems, and they have also developed the waste incineration technology and environmental protections technologies like flue gas desulfurization, identification, something like that. Then, end of the 20th century, they merged each other, and they have created two companies from the Steinmüller and Deutsche Babcock. One is the Babcock Borsig Power Energy, another Babcock Borsig Power Environment, in which we are now operating. And after 2000, the company is involved also NORCA-RC in this group. Also, they have also installed waste energy plants and environmental technologies. And 2002, the company is totally separated from the Babcock group and taken over by Italian company Fisia Babcock, and operated in 2002, started to operate under the umbrella of Fisia Babcock Environment up to 2014. 2014 is the company is taken over by the Japanese company Nippon Steel, and since 2014 we are operating with the name Steinmüller Babcock Environment. Very short historical information about our company. We are a middle-sized company.
Excuse me, Mr. Ali. There's some voice distortion from your side. I think it's because the speaker is the mic is quite close to your face. So if you could adjust it accordingly, so that would help the audio quality.
Okay. Okay. Now it's better.
That's fine.
Okay, now our company is a middle-sized company with a number of employees, nearly 250 people. Most of them are the engineers. We have, as average turnover value each year, about 180 million euro. Our mother company, Nippon Steel Sumitomo Engineering, located directly in Japan, Tokyo. And they have a number of employees, nearly 5,000 people, and with a turnover about 2.2 billion euro each year. The mother company of the mother company, our OPA company, is the Nippon Steel, second biggest steel producer in the world after Alcatel. And they have a number of employees, about 90,000 people overall in the world. Our head office is located near to Cologne in Gummersbach in Germany. We have also mother office is located in Tokyo. Overall in the world, we have some branches, some cooperations partner who taken our licenses. Our company is typical engineering company. We are making all from the waste energy plants components, all basic in detail engineering. And we have also a project management system for the execution of the project and quality and health and safety management system. Of course, we have the procurement and logistic organization system, and we are making construction commissioning. That means we are typical EPC company for the installing of such waste energy plants. Now we are coming to our core problem, energy from waste. How we can handle the waste, how we can produce energy from the waste. Now, worldwide, our company has 646 references until now. Most of them installed in Europe, second is in Asia. We can handle the municipal solid waste, RDF waste as a refuse derived fuels, industrial waste, biomass, sludge, and tires, hospital waste with several systems. We have 3 different processes in our house. One is grade incineration, another gasification process, direct melting system. The third one is rotary kiln incineration, especially will be used for the hazardous waste, for the hospital waste and animal waste. But we will give our focus more to the municipal solid waste in such countries like India, like Pakistan. Is most interesting to get more knowledge about this municipal solid waste, how it could be treated. Now I will introduce our waste energy system on this. The number one, what you see, it is our bunker. The waste, municipal waste, will be delivered by vehicle directly into the bunker. Into the bunker, waste will be mixed and prepared for the incineration. After the mixing, by means of cranes, will be put into the feeders number 2, and due to feeder and feeder hopper number 2 and 3, the waste will be delivered directly into the combustion chamber. In this combustion chamber, the grade system, the waste will be burned, incinerated, and also moved from beginning up to the end of the grade. During this process, all waste will be burned, all slag and not burnable materials will be removed from the system. After the burning, of course, we are producing flue gas and with a high temperature. And of course, we want to use this heat from the flue gas. And we are passing in the number 8 and 9 to the heat exchanger system. And we are heating the water up to certain parameters, pressure and temperature. And after this heated steam, we are producing steam. This steam will be connected directly to steam turbine and will be produced energy. And all residues, all slag will be removed from the system in the number 6, will be collected separately, slag in other near to bunker in other slag bunker, and residues from the boiler system, and after that is coming from the flue gas cleaning system, also will be collected separately and will be delivered to the landfilling. After the passing the flue gas through the boiler system, the flue gas is containing a lot of air pollutants. This pollutant should be removed from the system, like dioxin, like sulfur dioxide, like chloride. We have several air pollution control system after the boiler, but we are showing here a semi-dry system. Number 14 is our semi-dry reactor. We are injecting in the system calcium hydroxide for the removal of sulfur dioxide and chlorides. And we are injecting also active coals. Active coal is therefore injected for the removing of the dioxin. All cleaning of the flue gas happening in this area, in the number 14, 15, and 17. In the number 17, we are installing back filter. All residues from the which is coming from the reactor number 14 will be removed in the back filter, and also the ash content which is coming from the boiler or incineration system will be removed also by the back filter. After the cleaning of the flue gas, then the flue gas will be leaded directly to the atmosphere. It is a typical waste incineration process. More or less, a lot of companies are offering in that way. Of course, the differences from company to company you can find in the detail of grade system, in the detail of boiler design, in the detail of the flue gas cleaning system. We have also another process in our house. It is DMS gasification, direct melting system. But this process is mainly usable for the island countries because in this reactor, always put in a reactor together and melted directly by means of additional oxygen injection and coal injection regarding increasing of the temperature in the reactor. All waste will be melted, then from the bottom of the reactor you can get slag and metal directly from this system. In that way, the amount of the metal and slag is much less than by normal incineration process, because we have a temperature level in this reactor up to 1700, 1800 degrees. Of course, the flue gas cleaning system after this reactor, it is more or less the same like in the incineration system. But the slag amount on the comparison to waste incineration system in this much less than incineration system. This system is more expensive than waste incineration system in the operation or in the installation, but it makes sense if you have some island countries like Japan, like in other island countries, then you can reduce the landfill volume which will be needed also after the waste incineration system. I would like to show you a few highlights from our history, from our references. For example, we have installed one energy from waste or waste energy plant in Herten in Germany. We have installed this plant has 6 lines. From these 2 lines is for the hazardous waste and 4 lines is foreseen for the municipal waste. Hazardous waste is rotary kiln system, and the municipal waste is our normally forward pushing grade system, installation system. All lines are installed by our company, and we are producing 52 megawatt thermal energy each line, and another smaller line is producing a little bit less than this, and we are burning in these two lines, each line 17 tons per hour waste. Another one of our biggest waste energy plant we have installed in Italy, Acerra. We have 3 lines, and each line is foreseen for the waste amount nearly 30 tons per hour. And we are producing each line 113 megawatt thermal. Each line is connected to one steam turbine, and we are producing electrical energy for 3 lines together about 120 megawatt. One of our biggest waste to energy plant what we have installed until now. And I would drive your attention to the caloric value of this waste. It is one of the highest caloric value. It is 15,000 kilojoule each kilogram. Only in that way we could produce this high energy from our system with this 30 tons per hour. One of our other examples from Berlin, we have installed in Berlin one of the biggest grade system. Only with one line we can incinerate 36 tons per hour municipal waste. And we have a capacity of our boiler 90 megawatt thermal. This plant is installed as EPC directly by us. Everything is planned and installed and commissioned by our company. We were the general contractor. Another example in Lithuania, although we have one of the biggest grade system installed for a capacity 34 tons per hour. And the boiler capacity, what we have installed, 85 megawatt thermal. An example for the DMS direct matrix system in Japan, I want to show you. We have the 3 lines. Each line is foreseen for 10 tons per hour. And here will be between 9,000 and 12,000 kilojoule caloric value of the waste will be melted. I want to give you with this presentation a short impression how our company is working, which technology we have, how we can reduce the volume of the municipal waste, on which references we have. I hope it was useful for you. Thank you for your attention. Hello?
Mr. Ali.
Yes.
So you are finished with your presentation, right?
Yes.
Okay. Thank you very much, Mr. Ali, for a very detailed presentation on the work which your company is doing and the kind of plants which you are putting up, the technical specifications and everything. We have one question from participants for you. It says if the participant is actually from Pakistan, so he's asking, is there any way, a possible way to collaborate with Steinmuller Babcock to start commercial projects in KP province of Pakistan?
Just a moment, please.
Can you hear me?
Just a moment.
Okay, sure.
Following, sir, what is the work together? We are not now. We are this Pakistan and India is a new countries for us. We are investigating now in India how because you should also consider the cost of such plants and invest cost and operation cost. Now we have learned in India we cannot cover this cost in such countries because in Europe, look, we are paying for tipping fees if we deliver the waste to the such energy plants. But in India and in other countries, it is a little bit strange, bring the waste and then giving the money at the same time. And if you look the waste caloric value, it is in India, for example, and I am anticipating in the Pakistan the similar one, it is very low. If that means the invest cost is the same, but the produced energy is less. That means we can also not cover only with the selling of the energy, the operation cost and invest cost. Therefore, we have made the investigation. If some companies are interested in Pakistan or India to work with us on a license basis, then it is possible. We can provide our license and the one Pakistan company can design and install such energy from waste plants based on our license. Otherwise, we will be too expensive and we will never be successful.
Okay, so basically this question was asked by Mr. Mohammad Mansoor Yusuf from the KP government, and he says that there has been budget allocated for the waste to energy for power generation, and that was the context for his question. So what I can do is I can take the email from Mr. Mansoor and I can connect both of you guys, and you can see together if there is a commercial viability or whatever the idea is, and you both can take it together, and SARC Energy Center will be glad to help you out in facilitation. So moving on to the next question from Komal Shetty from India. The question is, what are generally the maintenance costs of incineration-based plants? If you can share a figure as a percentage of maybe the installation capital.
Maintenance. Yeah. It depends on a lot of parameters, of course, but you can very roughly, you can in the first 5 years, you can a maintenance volume 10% of 5% of investment cost, and then after that increasing, of course, because maintenance is depending on the waste quality. Maintenance is depending on how good or which quality you have installed the plant, designed and installed. Maintenance depends on how you are operating the plant. Therefore, we can give very roughly number. In the 5 years you can in the total assume 5% of the plant investment. After that, of course, it will be increased. If you are burning a lot of plastics, for example, you have higher maintenance value. You are producing more energy, but higher maintenance value because of chloride concentration. Okay.
Thank you very much. So these were the questions from Mr. Ali Disbe. Thank you, Mr. Ali, for joining us. I will connect you with the particular resource person who asked the question and wanted more details about the
Okay.
possible collaboration. Moving on to our other presenters, just want to check if both are available so that we could go ahead and proceed with our remaining questions. So, Mr. Johansson and Mr. Peters, are you there?
Yes, we are. Yes, I'm here.
Yes.
Okay, thank you very much. So one by one,
Okay.
I will go through the questions. First, I will go through the questions from Mr. Stephen Peters, so that there are some questions in the queue. So the first question is, can you please explain few key operational challenges, especially for plants in SAARC region, and the main reasons for them not achieving the required PLFs? This question is from Mr. Aditya Parchur.
Okay, sure. There are a number of reasons, and some of them are sinister and sad and disappointing. For instance, I went to a wastewater plant and half the equipment had been stolen and sold, and that was so disappointing to see. And then there have other problems where you have difficulty attracting people and retaining people to operate the plants. This is more a problem in the Pacific region, but it is a problem in South Asia, where you train somebody up how to operate a piece of equipment and then they go and work somewhere else, or they go and work in Europe or the US where there's more money. So those are the two real challenges. In terms of the technical side, the challenges aren't really operational. To be really frank, in South Asia, one of the challenges we've had is the counterparties, how getting paid by counterparties and the financial structures. They have been the dominant themes that have come through in projects that I've seen.
All right. So we have Mr. Salman Azad and Mr. Amir Bhatt from the Punjab Power Development Board in Pakistan. They have asked a few questions. I will go through them one by one. The first question is, basically they are setting up a 40 megawatt waste to energy power plant in Lahore. So their question is, can you please share some lessons learned recently in South Asia, in particular for incineration based municipal solid waste power projects? For example, the highest proven efficiency or the tipping fees, etc.
Okay, in terms of operational efficiency, there's not much data because there's not many incinerators in South Asia. In terms of lessons learned, one of the great challenges is dealing with local pressure groups, NGOs, and also those people who've been disenfranchised. Their source of income has been disenfranchised by the creation of an incinerator. So, for instance, in Pakistan, a large number of people who do the waste sorting on dump sites are actually Afghan refugees or displaced Afghans or Afghans who are illegal immigrants. And so there is a challenge that you need to manage that process. And I think I understand that it has to be managed across a range of areas, but the situation in South India is a little bit harder. From a social point of view than perhaps, certainly than perhaps Europe. Europe and Australia and to a lesser degree the US are stricter environmentally, but socially the challenges are stronger in South Asia. The other issue in terms of efficiency,
Sorry if I may ask, what kind of social challenges are you referring to?
Okay, so say for instance, I was in Karachi 6 weeks ago, and I had a great. I was spending some time on a dump site, and had a chat away to some of the chaps who were working on the dump site, and some of them were quite young, some of them were 10 years old, but the challenge is that those people are employed and engaged in the activities of transporting waste and sorting waste. When you put in an incinerator, you take out that portion of the economy, you take out some of those jobs. Now, when you train people up, they're not going to be from that sector. They're going to be university graduates who are Pakistanis or Indians or Sri Lankans or Bengalis who are from their own particular country. So you then have a situation where you have to deal with social change. So much to do with waste has to do with social change and managing urban populations. not from an environmental or energy point of view, but from a social point of view. I can't stress how strongly that is important, and that is a determining factor in the success or otherwise of a waste to energy plant outside of OECD countries. So you need to think about and plan and engage with communities so that those communities see they get a benefit, and that those portions of the community that get disadvantaged are compensated or are drawn into the project in other ways. Project design is not just technical and it's not just financial. It needs to have the environmental and social safeguards.
All right. There's question, what is the impact on calorific value of municipal solid waste if the same is stored in a pit?
It'll dewater. So in other words, it'll start to, the organics will break down and it'll dewater. You'll lose some of the calorific value of the solids, but you will also increase the water content of those solids because intercellular water will be released. So in short, if you want to put it in a pit, you want to leave it in a pit for a few days, then shake it off and then use it, and preferably sun dry it.
All right.
Sorry, I got to add on to that. Or if you're in an incinerator waste pit, the guys who are trained to operate those waste pits are trained to let those things dewater and then pull them out and then put them in at the right time. So to let them go off for 2 or 3 days. So you'll see, if you meet anyone who's worked the cranes in those large incinerators, they'll tell you how to do that.
All right. There was one question regarding the fluidized beds, which you mentioned in your presentation. The question is that why fluidized beds are popular in Russia? Is there a particular cost or quality related reason?
Okay, I think the third speaker might be better at answering this question than I am, because I'm not an expert on fluidized beds. But my understanding is Russia has a lot of people who are trained in the oil and gas industry, and this type of technology is really almost technology from the oil and gas industry, or at the same technology level as the oil and gas industry. So as a consequence, I think the Russians feel a little bit more confident with it. That's what I expect. But I don't know. I could ask Mr. Ali may have a better answer to that than me, or Inga might have a better answer than me on that one.
So I will move on to Mr. Ali or Mr. Engi if they want to answer this particular question.
Can you repeat please the question again?
So the question is that the fluidized bed, why are the fluidized beds popular in Russia? Is it a particular cost or quality related reason for this? Or we may make it generic and say why the fluidized beds are popular, or what's the strong points for this kind of technology?
No, the gasification process always the companies who is designing and supplying such process trying to find some markets, of course. They are making some appetite, but in the reality, last time in New Delhi, I was in a conference from NTPC. Also, two companies has presented their gasification process. One is the plasma technology from Westinghouse from US, for example. But as a result, I can tell you, forget such processes in such countries. It is in Malaysia or Japan or in other island countries. I don't know, Madagascar. I don't know. I cannot remember. Or Canarian Islands, etc. Perhaps you can do it because the remaining volume of the waste which should be brought to the landfill is less than by incineration plants. But all of gasification technologies which you can choose, it is more expensive than incineration plants. Therefore, my suggestion, we have the both product. I can make you appetite for the both, but if I will be realistic, then I will say you follow on the incineration system. Even if we have the big problem to cover the Indian or South Asia cost, they want to pay for the investment, not this amount what will be paid in Europe normally. And we are trying how we can realize this. Yeah, it is imagine in India they are speaking about 30% of the investment cost should realize from Europe should realize in India. We have to save 70%, and how we can make some thoughts about the gasification.
Right. We have a comment from Mr. Aditya Parchur. He's from India. His comment is for Mr. Ali. He says that would you be interested to invest and partner with a strong co-investor in India to set up a waste to energy power plant on a build, own and operate mode? So I feel that he belongs to a particular company, and at the end of the session, I will link you both up so that you can further explore the possibilities of having a co-investment for setting up a plant in India. So moving on to another question. This question is, what are I guess this question is from Mr. Peters. What are the instances where supplementary fuels are used?
Okay, so could you put that into some context? What type of technology are we talking supplementary fuels? Are we talking about adding coal?
The questionnaire has not actually specified, but I feel this is mostly related to the RDF kind of fuels which you mentioned.
Yeah, okay. All right, so when you're using RDF in cement kilns, it is a supplementary fuel anyway. If you're talking about having a number of biomass plants, depending on the technology you use, empty fruit bunch is difficult to burn. Let me finish. Sorry, let me finish, because this is a point that's important to make. That you will sometimes burn palm kernel shell, and in some cases they even burn coal. Now, we have a problem with burning coal in our bank. We're not particularly keen on people burning coal as a co-fired fuel. So that's why I asked that question. Sorry, Umar.
Okay. So no problem. So the questioner has specified that he's actually talking about the incineration technology and for the municipal solid waste.
Okay, sure. So a great example that would be the incinerator built by CNIM in Baku in Azerbaijan, where the waste in Azerbaijan turned out to be not particularly strong calorific value. I don't know how they got that wrong, but they did. They built the incinerator and they couldn't get it to operate at the temperature. They just happened to be very, very lucky that Azerbaijan has a massive natural gas reserve, so they could co-fire natural gas in it. And natural gas in Azerbaijan is actually lower than the spot price in New York for bulk transfer. So co-firing of fuels is normally done, of municipal solid waste is normally done when the waste is not particularly a high calorific value. We have a project in the Pacific Islands where we have a small amount of municipal waste, but we have a large amount of waste engine oil from the shipping fleets that go through that area. So as a consequence, those two can be co-fired. It means that it's co-firing them with waste oil has implication on how that project is viewed regards to climate mitigation and also to whether or not it's renewable energy. So there are implications to how the project is viewed, how it's funded, and what concessions and grants might be available to it.
Okay, thank you very much. So next question, moving on to Mr. Johansson. The first question is, how strict are the emission standards for incineration-based waste-to-energy plants in Sweden? This question from Mr. Bilal Hussain from Pakistan.
Generally, the minimum requirements are set by the European legislation. Then you will have in each plant will have their own environmental permits regulating the emissions, and in some cases those emission limits are more strict than the European framework, especially when it comes to emissions to water. They are normally a lot more strict than what European regulation sets. It also depends a bit on the local conditions for the plants and on which technology they use. I know that the plant I showed a picture of in the southern of Sweden, for some of the effluent water, they have stricter limits on metals than what you have as a guiding value for drinking water in Sweden. So they actually could have they could break the law by having a leakage of drinking water from the drinking water pipes into the effluent. So you can't say that everyone doesn't have necessarily the same, but the minimum standard is the European that's set in the Industrial Emissions Directive and also in the now BREF documents that's being updated, where they will have some additional changes.
So I'm assuming you wanted to give an answer to the fluidized bed question as well. So you want to talk something about that?
Yeah, I can say we consider in Sweden you have only 25-30% of the waste to energy capacity is in fluidized bed boilers. There have been different reasons for that, but if you look at biomass-fired boilers, I would say that all larger biomass-fired boilers are fluidized bed boilers. They have a very good combustion, and normally they have a small area footprint because you can build them more on height than you do on the grate-fired boilers. However, you need a more advanced fuel preparation plant which will offset that gain. Normally the CFB boilers are also less expensive if you don't include the fuel preparation parts. Then they are less expensive when coming to investment costs. However, they are not as robust as the grate-fired boilers. You have a larger demand and it takes a bit more skill to run them. And you can also achieve like much lower NOx emissions on a fluidized bed boiler than grate-fired boiler. So there might be a number of different reasons for using a fluidized bed boiler. I might also mention on the co-incineration, actually in Sweden you have seen biomass plants co-incinerating waste because the biomass is getting too expensive. So then they want to add a fuel that's less expensive. They will have to add on investments in flue gas treatment and some rebuilding of the plants sometimes, but depending from case to case, that might be economically viable.
All right. There are two more questions for you. First one is it right to assume that landfill tax could not accelerate the municipal waste usage in waste to energy applications in Sweden? And what are the key learnings we can derive from it? This question is from Mr. Atikur Rahman from Bangladesh.
Could you repeat the first part?
So he asked, is it right to assume that landfill tax could not accelerate the municipal waste usage in Sweden?
The landfill tax right now is put on those waste amounts that's not covered by the landfill ban. So we have a landfill ban on combustible waste as well as organic waste. But then you have some waste that's still going to landfill, and those are covered by the landfill tax, which is roughly 45 to 50 euros per ton. I think the landfill ban played a stronger role in diverting the waste from landfills than the tax did, but the tax was the start of it. And the tax also especially affected the industry to divert waste from landfills because all of a sudden the landfill wasn't the cheapest option anymore. So I guess we do have the gate fee for landfill, including landfill tax, will probably be somewhere around 100 euros per ton. And an average gate fee for an energy from waste plant is maybe between 40 and 50 euro per ton.
All right. So the second question is, it's sort of a comment basically that in Sweden the waste to energy plant is paid money for waste collection, but the opposite is true in many countries where the waste to energy investor is asked to pay in order to purchase the waste. So my question is this true? Is this comment true, or like can you please elaborate?
It depends on what you mean with a waste to energy plant. So if you would look at the waste to energy plant burning like kernels or agriculture or forest residues, they will pay for the fuel. If you look at plant receiving industrial and municipal solid waste, they will normally have a gate fee, as I said, somewhere around maybe 40 or 50 euros per ton of waste. So I think that income will come from both the gate fee and the energy they produce. There will not be any plants available or viable in Sweden that would accept municipal solid waste for a zero gate fee on a long-term contract. You can have certain waste fractions that can be accepted for zero gate fee if they need to fill up the capacity to utilize the plant optimally, but not in the long run as it looks now, at least. The energy prices are too low for that.
All right, thank you. Nimal Pereira from Sri Lanka asks, is there any, so this question is from both you and Steve. Is there any reference website to obtain emission standards for waste to energy plants? Can you recommend any resource?
Yeah, I can. If you have a look, GB standards for China, the EU directives are very easily identified online. Japan's Japan's emission standards are published. Who else has published? I don't know about the EU standards. I'm not sure about particular countries within the EU. I think they would follow the EU directive. Would that be right, Inga?
Yeah, in general, they're obliged to follow the EU directive. So, but they might, since it's an environmental point of view, they can also adopt stricter requirements. I think the US EPA also have emission limits online.
Yeah, I would be suggesting you look at the Japan and EU emission standards.
Yeah, I think that those are applied in quite a lot of other countries as well.
Yeah, they're a lot stricter and a lot more thorough.
All right, thank you. The second part of Nimal Pereira's question is there any recommended sustainable economic model to study the feasibility of waste to energy project in a particular place or particular country? Has anyone developed done any modeling?
Yeah, there is. There's tons of proprietary modeling. All the developers have their own models. I know KPMG built up a whole bunch of models as well with various inputs in terms of manpower, cost of fuel, makeup mix, moisture content, and then they applied particular boiler solutions to it. But those models are normally proprietary to the owners.
Okay, all right. So there's no publicly available model as of now.
Not that I'm aware of, no.
Okay, thank you. And the final question is from Mr. Haider from Pakistan. He is asking, are there any viable options to use heat recovered from waste to energy plant in relatively hotter regions such as Karachi or Lahore?
Yes, there are. You use an absorption chiller. So basically what you're doing is you're turning the heat into cooling, and that can be used for providing cooling, for instance, for cattle at Baines Colony, or looking at doing in Karachi, or providing cold stores to people who are shipping fruit.
All right. So with this, we are finished with all our questions.
Umar, could I just ask? Sorry,
yeah,
Umar,
sure,
could I
please.
just make one point in request?
Sure.
Inga was asked a question about cost of waste. What we're seeing is that the cost of generally unsorted waste that is a cost. But there are apps and solutions which are coming out to displace the existing centralized collection of waste to Uberize, much the same as Uber changed the taxi industry to Uberize the collection of waste. And in South India, to South Asia, that will have a direct implication because that will engage and empower those communities that are possibly going to be disenfranchised by larger incineration projects. The numbers come out that there's a 25 to 35% saving in cost to government for collecting waste using that model instead of using a centralized trucking model. Now, what that then means is that you will have some waste which is sorted, which will be valorized, will have value, and other stuff that won't. So it will have an implication in the waste to energy models. So in that way, we're actually in the beginning of a change in the economics of waste to energy and how we look at it, because we may be in a situation where people will be paid to collect that waste which is not being collected at the moment. And some of that may even be done by donors, not just governments, but external donors. For instance, in the case of Indonesia, where there's an enormous amount of plastic in the ocean, people will pay internationally to help Indonesia clean that plastic up. That's what we're seeing at the moment.
That is a perfectly innovative model. I feel that some sort of this activity is already being done not legally, but like in out of the legal realm, like you mentioned, the Afghan refugees or the people who are picking waste and they're sorting the waste. So this sort of pre-sorting is already being done, but the model is not being established by the government, and I think the government needs to play its role in order to monetize this activity and establish tariffs and rates for such kind of sorting. Do you think that this pre-sorting or I would say collection of particular kind of waste will it have a future in the urban areas of South Asia, or is it mostly related to the regions where the waste is dumped?
Okay, so what I'm seeing is that when you have price discovery and a market on a particular commodity, then you have a consistent value, whether it's soybeans or milk or gold bars or iron ore. Well, sorted clean plastics will have the same. Currently, a lot of the plastics that are recycled in Pakistan go off to factories where they're burnt in open boilers to make in the textile industry. And so the pollution from those locations is tremendous. So they have no emissions controls, they burn plastics openly, and you can't even get into those locations because they know they're breaking the law. In terms of how that will affect it, is that you will have a situation where those Afghan refugees or those small to medium enterprises or those people who are not actively engaged economically, so they're not unemployed, but they're underemployed or under-engaged, that section of the community will then be able to have decent price discovery and will be in a position where they can be incentivized to collect waste which is not otherwise being collected and is flowing to the sea. That's a big change that's going to occur over the next 5 years. There are already 2 companies we know working on apps and working on solutions to make that happen. And one is going live sometime in Q3 in the Philippines. Another one is already working in Malaysia, but is not as advanced as the unit in the Philippines.
Perfect. So just to mention here, we have students from 2 universities. One is the National University of Science and Technology, and second is the UPCASE in Peshawar. They were also listening to your presentations, and this they were participating in this webinar, and they might also have a few questions which we would share with you in email in the coming days as well. So with this, I would like to thank our presenters and experts who took out their time, despite the program was a bit mismanaged because we were hoping to finish it by 1 a.m. but now it's almost 1:45 a.m. Many apologies for that. But it shows the interest of the people, the amount of questions which we have received. It was tremendous as compared to previous webinars. There was a lot of interest in this webinar. The experts, they shared very relevant and important information with everyone, and of course this led to the interest which was just generated in the participants. So with this, I would like to conclude our webinar and would like to thank everyone for attending today's session of the webinar. The presentations were excellent and they were delivered by our distinguished presenters. All the presentations, we would make them available on the SARC Energy Center's website very shortly. And we would love to hear from our experts and from our participants for any suggestions and comments for further improvement, or any suggested topic of your interest on which you want us to arrange future webinars. We would, as a center, we would gladly do that. Once again, I would like to thank our distinguished panel of experts. If you want to say any parting words.
I'll go first because I was the first speaker. Thank you very much for spending time with us this afternoon. I look forward to your questions and I look forward to doing more work in South Asia.
Thank you, Steve. Mr. Johansson, would you like to say anything?
Yeah, I also want to take the opportunity to thank you all for listening and posing interesting questions. I also look forward to getting more questions, and it's interesting to hear what's going on in the region and to follow the development further on.
Thank you very much. Mr. Ali, he left because of some meetings, so I will be connecting him with the relevant people who were asking few questions and wanted to collaborate with this company. So with this, I would sign out and thank you once again for joining us today, and we'll look forward to seeing you next time. Goodbye and have a good day.